thank you very much, Giovanni and Lucia. In fact, I should start with a disclaimer. I learned only this morning that I get the honor to speak today in this PetaSpin seminar because my student Merta Chudin, who was actually supposed to speak, unfortunately is on sick leave. So thanks again, Lucia, to make sure that I don't have a boring day today and that I could here present instead of Merta. And with that, I also hope you forgive me if this talk is not maybe as polished as talks would otherwise be. All right, so what I want to do is give you a bit of an update into our ongoing experiments in NV magnetometry of essentially two types of materials that you heard already about, antiferromagnets and 2D ferromagnets, which I think are particularly rewarding samples or materials to look at with NV magnetometry, because here really I think this new technique brings added value over what is around already and gives us new insights into these materials, which are very difficult to obtain otherwise. And I hope I can give you a few examples of this throughout my talk. So I will not give you an introduction to NV magnetometry. Luckily, others have done this before. I want to comment, however, on one point which maybe wasn't discussed so much up until now. I mean, you've heard about all these beautiful features of NV magnetometry, such as it being quantitative, non-invasive, the spatial resolution, what have you. But we haven't really talked so much about sensitivity yet. So sensitivity tells you how weak a magnetic field one can detect using NV magnetometry. And the point I want to make is that what is nice about using here a quantum spin for magnetometry is that ultimately its sensitivity is really only limited by the laws of quantum mechanics. So if you look into this process of measuring magnetic fields using spins, you will find that this is limited by quantum projection noise. And then this quantum projection noise limit, where the readout of this spin again is limited by the quantum postulates of measurement. It's given by this formula here, which essentially contains the gyromagnetic ratio of the spin you use for magnetometry, and here the square root of the coherence time, the quantum coherence time of that spin. And that is for all or most practical purposes, this is mostly on the order of 1 microseconds. And if you plug this in, you see that an NV magnetometer, a single spin magnetometer like this, can achieve sensitivities on the order of 60 nanotesla per square root of hertz. So it can resolve changes in magnetic field of about 60 nanotesla within 1 second of data acquisition time. That, of course, requires that you can implement such a quantum mechanical measurement scheme and this projection, quantum projection limited sensitivity, which in our case is limited by the efficiency of this optical addressing of the NV spin. So you've heard before that we perform optically detected electron spin resonance in these measurements, and how well we can address the spin therefore depends on how well we can here couple the fluorescence that is emitted from this NV spin to our detector that's sitting somewhere above the scanning probe. And so I will just take one slide to show you a little bit where we stand in the field in our progress towards reaching this spin projection noise limit, and what type of engineering that we're doing to improve the sensing performance of these scanning NV magnetometers. So you've heard already in Vincent's talk before quite nicely, where this whole technique comes from, so that this idea of scanning NV magnetometer really originated from this work by Chernobrod and Berman from 2005. And then the first implementation of this idea, in fact, comes from Stuttgart, where Rainer is working, and was first shown using these essentially grafted nanodiamonds on scanning probes. And this was very nice for proof of concept, but really was still far from this optimal spin projection noise limited sensitivity by close to 2 orders of magnitude. So this is where essentially I started entering into this field when I was still a postdoc with Amir Yacobi, and when we introduced these scanning probes that you've already now seen advertised several times, in particular also by Vincent. And here I just want to mention that next to these pillars being robust scanning probes, they're really photonic nanostructures. We engineer them such that they optimally guide this NV fluorescence to our detector and thereby improve sensitivity. And using this first generation of these tips, you see we improved here by roughly factor of 3 or so. and approach further this fundamental quantum limit. Here, I just want to give you sort of the latest generation of these scanning probes that we engineered with my group in Basel. The key here is not to work anymore with these cylindrical tips, but rather to shape these tips into parabola-like reflectors, as you see here. And with these, we could drastically improve this further. We're now down to a photon collection efficiency of about 12% with these, and just about a factor of 7 away from the best we could possibly do using these scanning NVs. And of course, we keep working on that. I just want to advertise also, since this session is organized by Konami, that this technique has been patented and is also now exclusively available at Konami as special scanning probes. All right, so these developments over the last year, they really allowed us to implement by now quite a range of scanning NV magnetometry applications. Here you see a bit of a gallery of the type of materials that we were able to address so far. And you see that this not only spans a quite wide range of physics, but also a range of temperatures. So this all works at room temperature, but almost equally well under cryogenic conditions. And so today I'd like to just dive into 2 of these application examples, one being a room temperature application and the study here of antiferromagnets, and the second one being a low temperature scanning NV magnetometry example in the case here of these 2-dimensional so-called Thunderwalls magnets. And so I'd like to start here with the first case, namely the one of the Thunderwalls magnets, which were already introduced beautifully by Rainer. So I can be rather quick on my introduction, I believe. But just to recap, what we really like about these Thunderwalls materials in general is their ability to engineer materials properties, for instance, by stacking, twisting, or then combining materials of very different sort. And magnetic Thunderwalls materials are, of course, no exception to that. But what is special is that they haven't been around for so long. They were only discovered in 2017. And in fact, the first of these magnetic Thunderwalls materials that was realized or experimentally addressed was this material here, chromium triiodide, that you already heard of from Rainer before. And here's just sort of an overview slide of the key properties of these materials. And with this, I'd like to highlight that initially the community really focused on using magneto-optical Kerr effect to study magnetism in these materials. This is quite convenient because it's an optical method and readily implemented and works for out-of-plane magnetized samples. But of course, it suffers from various drawbacks, such as it not being quantitative and also having a limited spatial resolution here in the optical range. Now, one big question that came about already with these very first studies of chromium triiodide has to do with the layer dependence of magnetization in these materials. Namely, it was shown, and this is you see the data over here, that for chromium triiodide, one could see an even-odd effect in the sense that odd numbers of layers here showed, typical hysteresis curve that you would expect for ferromagnetic sample, whereas even layers of these materials did not, and in fact showed no remnant magnetization here. So you can of course readily explain that just by postulating that adjacent layers show an antiferromagnetic interlayer coupling. The problem with that was just that this explanation is at odds with what is known about the bulk of chromium triiodide, which is a bulk 3-dimensional magnet. And this was one of the questions we wanted to address with our measurements and which motivated these experiments at first place. All right, so here is maybe the key results of that. So what we worked with were these exfoliated samples that we gotten from the more Pogo group at the University of Geneva. Here's one example of a flake that was exfoliated into 2 regions here, one being a tri-layer and the second one being a bilayer flake. And here you see the results we get when we scan our NV magnetometer or our NV center over these flakes with the technique I don't need to repeat. So essentially what you see here in color code is the stray magnetic field projected onto the NV axis. And you see right away that these data also confirm this even-odd observation, namely that we see sizable stray magnetic fields emerging from this odd layer numbered part, the 3-layer part, whereas there's close to 0 stray magnetic field here on the bilayer. And now again, as discussed already in previous talks, one can in fact reverse propagate these data to the source. One has to make certain assumptions in this, but in the current. Can you hear me again? I had a sign that I was muted. I know, do you hear me?
Sorry, it was a mistake.
Okay, good. So what I was saying, I'm not sure if this was muted already, is that one can reverse propagate these data. And in the case here of a uniaxial out-of-plane magnetized sample, this is in fact a unique mapping that allows us to recover the underlying magnetization pattern in this material. And again, it just confirms what I said before, 0 magnetization on the bilayer and a magnetization of about 15 spins per nanometer square on the trilayer. And by the way, this number matches very nicely with what was expected with this material to begin with. All right, so we carried on and looked at a range of samples, and it was all confirmed in the sense that, for all the odd number layers, we saw a magnetization which was non-zero and identical for all these samples, whereas all the even numbered layers showed zero stray field and 0 magnetization. So this question of this even odd effect in fact persisted, and for some time we were still puzzled by that. Now, luckily, there was an accident in one of our experiments, which allowed us to shed some more light on this issue. And the accident was as follows. So here you see an AFM scan of one of the samples that we looked at. In this case, it was a 5-layer sample and a 9-layer sample next to each other. And one night, late at night, my student Lucas was scanning the sample and accidentally crashed the tip into the sample. And you see here this type of destruction that this caused. And initially, we were quite disappointed. We thought this would essentially destroy the sample and stop the measurement run. But that was not the case. Instead, what happened after this puncture was that we observed that the magnetization was increased by puncturing this flake. And you see this here just by line cuts across these edges, how the magnetization or the stray magnetic field strength here increased essentially by a factor of 9. And now, of course, this increase by a factor of 9 is indicative in the case of a 9-layer sample that we turned this antiferromagnetic interlayer coupling into a ferromagnetic interlayer coupling. So that's what the data suggests. The question is, of course, why that happened. And the reason for this is something that Rainer already alluded to some extent. It has to do with the stacking order of these different parts of the flake. And we were able to really to verify that using Raman spectroscopy that we performed on these 2 parts of this flake. So again, the good thing here is that these were separated with a 5-layer part, which was decoupled from the 9-layer part. And you see here that there are, well, weak, but still clearly distinguishable differences in the Raman spectra emerging from these 2 parts of the chromium triiodide flake. And as it turns out, if you look into literature that is existing on this material, these 2 Raman spectra are consistent with 2 different stacking orders, one being monoclinic and the other one rhombohedral. And then again, if we go back to theory and compare to the expected interlayer magnetic coupling for these 2 cases, one sees that the monoclinic stacking is supposed to be antiferromagnetic, whereas the rhombohedral leads to ferromagnetic stacking. So this is for us the explanation for this even odd effect. So what we believe is happening is that by encapsulating these samples, and I should have stressed that these samples all need to be encapsulated so that they remain air stable. By encapsulating them, one essentially exerts pressure onto these samples and prevents the stacking order from assuming its natural order, so to say. So we know from bulk that bulk chromium triiodide has this rhombohedral stacking. This does not seem to be the case for exfoliated encapsulated samples, and this is why we get this antiferromagnetic interlayer coupling. And puncturing the flake the way we did appears to have released this pressure and therefore allowed the system to relax or return to its native state. All right, so maybe this slide here I skip. Rather, I'd like to take some time to talk a bit about some rather recent results. So we continue studying these 2-dimensional magnetic systems. And one recent focus of ours was to turn our attention to this material here, European germanium 2, which is a two-dimensional magnet of this silicene family. And what is nice about this material is that it can be MBE grown, and therefore it's possibly a scalable platform for future technology developments. So essentially, European germanium is in the bulk is an easy plane A-type antiferromagnet, but in the few layer limit, it has already been shown by sort of ensemble measurements that it's an in-plane magnetized soft magnet. So we want to study that essentially to see how much we can find out about this material and whether we can add some more engineering, so to say, by the fact that this is an MBE grown silicon-based material. So here we had to introduce some essentially boundaries to this material in order to get stray magnetic fields out of it. And the trick we played was to introduce mesas into this surface. So we essentially etched or patterned this two-dimensional magnet into mesas of various shapes, where then stray fields would emerge, and that would allow us to address the magnetism in this material. And here you see two such examples. Once on a monolayer of European germanium and once on a bilayer. In both cases, this sample was patterned into this circular shape. And here you see the respective directions of NV orientation and bias magnetic field. And you see right away that while we can obviously detect magnetism, we can also see some inhomogeneities in this magnetized layer. But maybe more importantly and more interestingly, we see stark differences between the monolayer and the bilayer. If you look closely, and that's maybe one of the values of this being a quantitative method, you see that actually the monolayer appears to be more strongly magnetized than the bilayer. But the bilayer does not give zero magnetization. So it's not the same thing as we saw before with chromium triiodide, where you have just antimagnetic stacking. Somehow this material, conversely to chromium triiodide, seems to transition more gradually from this ferromagnetic coupling in the few layer limit to the antiferromagnetic coupling in the many layer or bulk limit. So this is something we're currently trying to understand. As I said, this is preliminary data. We're trying to understand how this magnetization essentially evolves with layer number. And one thing I can also say here is that the stray magnetic field, if we analyze this quantitatively, is not compatible with a homogeneous layer of magnetization. There must be some canting happening in this material, which again, we're trying to understand. And here, by the way, just to also quantify this more, this is just a magnetic field dependence of this magnetization strength here. And you see once more that actually the bilayer saturates at a lower net magnetization as compared to the monolayer. Another thing we're doing is we're trying to see to what extent by changing these mesas, so changing the geometry of these magnetic layers, we can actually possibly engineer the spin textures that are stable in this material. So one thing that we've recently seen is, and this is again very preliminary, first indications of possibly introducing shape anisotropy using in this patterning. And here's what I mean by that. So here, this is again data on a bilayer. It's the same sample you've seen before. This is the circular sample, but we also prepared ellipses, which you see here. And the remarkable thing is that, so you have to realize that the magnetization obviously in this sample points in this vertical direction. So it just follows the external magnetic field. And it's something we've verified with a couple of independent sample preparation steps. So in this experiment here, we have this ellipse where we apply a magnetic field along the short axis of this ellipse. So if the magnetization was free to rotate in this layer, it would just follow this magnetic field. But that's not what we observe. Instead, we observe that the magnetization seems to be slightly canted here, or not canted, but rotated in this orientation. And our present tentative explanation is that this is due to shape anisotropy introduced by this elliptical shape. But again, this is something to be verified further. One goal for us is to use this and go a few steps further to, for instance, help us nucleate domain walls in this in-plane ferromagnet and then study the nature of these domain walls. All right, so now I want to go to spend some more time on this additional topic of using NV magnetometry to study antiferromagnets. Now, I must admit, I lost track of time a little bit. I think I started a bit late, but Giovanni, can you maybe tell me how much time I have left?
Yeah, 2 minutes.
2 minutes. Okay, well, then I'll be rather fast and speed up, so sorry for that. But I do want to maybe also highlight one recent result, and I'll be fast, on studying this antiferromagnet chromium oxide Cr2O3, which is a rather interesting material system for implementing antiferromagnetic spintronics technologies. That's on one hand because this is a material that orders at room temperature, but more importantly, it is a magnetoelectric antiferromagnet, which means that you can actually manipulate the order parameter using electric and magnetic fields. And as it turns out, the fact that it's magnetoelectric also brings with it a very nice property, namely that there are uncompensated spins on the surface of this material, whose direction is linked to the direction of the underlying nail vector, and therefore allows us to address this material. So we studied this a few years ago, initially on thin film. So I'll be rather fast here. This is just an example of how we could measure how this material transitions from paramagnetic into antiferromagnetic at this transition temperature of roughly 30 Kelvin, and how this breaks up into domains. Again, here this was on a thin film, and in this work that's cited down here, we're able to essentially investigate why there is domain formation in thin films of chromia. More recently, we were interested in studying the more fundamental properties of these materials, and therefore turned our attention to single crystal samples. And there, our motivation was to nucleate individual domain walls using the magnetoelectric effect. So I'll skip the details of that, and then study the properties of these domain walls. And that's something that worked. So here you see an example of a scanning NV magnetometry image of this single crystal of chromia. What we did again was to pattern the surface into mesas so that we get some stray fields out even in a part of homogeneous magnetization. And these are these mesas that you see here. And then by, again, magnetoelectric polling, we were able to introduce these domain walls into the sample. I should say without such polling, there were no domain walls, and that's not a surprise because after all, for bulk single crystal antiferromagnet, there is no energetic reason to form domains. All right. These domain walls, they were rather straight, in that sense, maybe boring, but also nice because it really showed that this is a rather pristine system where pinning of the domain wall is negligible. However, something interesting happened, and here I really just want to show this, and then I'll wrap up. Something interesting happened when these domain walls actually crossed the mesa structures, and that's something I show you here. So here's a zoom in into one of these mesas, with the domain wall going across, and you see that there is a behavior of this domain wall trajectory that really looks like refraction in optics. So obviously, the domain wall, the mesa is able to deflect the position of this domain wall. And first, we were puzzled by that, but then in hindsight, it's actually rather easy to understand. This is just the analogous of Fermat's principle in optics here applied to domain walls. So the reason why you get this deflection is simply because the domain wall, of course, has an energy cost, and by crossing the mesa, the domain wall positions itself such that it minimizes the domain wall energy, or rather the domain wall surface. It's something we were able to also retrace or simulate here with a spin lattice calculation with some of our collaborators. So this is not a drawing, it's an actual calculation that matches very nicely this type of trajectory. Okay, so with this, since I am so late, I'm sorry for that. I want to wrap up. We did push this a bit further. Let me just bring this across, and proposed a new architecture for an antiferromagnet-based memory, which is based on such engineered pinning sites based on such mesas, which could pin domain walls and therefore allow you to encode logical zeros and ones by the path the domain wall takes along such a mesa. We also showed this in first proof of concept. Again, if you want to know more about this, then I'd be happy to take your questions. So with that, I'm at the end. I'm sorry if I took a bit more time, And I thank you again for this very nice workshop. So thanks.